All right. I think let's get started here. Um, Hello, everyone. Welcome. My name is Suji Maniam. Do I have video here? Let's see. There we go. That's me. Hi. Some of you know me from Elephant Scale. So we are hosting this session right here. Let me share my screen so I can walk you guys through some of the logistics. There you go. Right. Excuse me. There we go. That's what I wanted. All right, guys. So thank you for attending. I know we have a few more people trickling in, but we should get going and get started. Thank you, guys. This is the machine learning engineering kind of a webinar / class, right? So some of the logistics I have sent you guys. This is the URL right here. So I hope you guys are all able to access the URL, and I see you guys coming in here. That's great. So basically, everything we are going to put in this doc, right? So there's no need to take notes or anything. Everything will show up here. And we are running this class as a weekly series. So basically every Thursday, 4 to 6 p.m. And here's a Zoom link for the class. We are using Zoom for our meeting. So just one click, just sign in, and then you should be able to attend the class, right? Very good. And let me show you something real quick. So this is part of our learning series. What we are doing is actually launching a couple of learning series, basically aimed at focusing on some of the practical aspects of things like machine learning and DevOps. So if you just click on the link, you will go to the main series home. And if you want to get notified for future series, please go ahead and sign in, and we'll keep you guys up to date. And also we'll send the recordings to people who are signing in, right? So good thing to sign in so you get notified. And this particular series is called Machine Learning Engineering. Let me talk a little bit about this in a second. And this is what Mike and I are going to be running today. Okay. And I'm walking us through the doc right here. So very quickly, we're not going to spend too much time in marketing. This is Elephant Scale. What we do is training. Mostly if we focus on enterprise training. Our topics are AI, big data, and cloud technologies. So, and that's why you see the series focus on those topics as well. Basically, what we do is we do instructor-led, on-site or virtual training. Actually, now with the coronavirus, we are doing more virtual because everybody is working from home, right? So, and also we are running some very discounted classes because we know a lot of our audience asked us to run classes because they are either home or they are not working. So the next class coming up is Google Cloud for Data Science. This is coming up this Saturday, right? So again, these classes are running on weekends and weeknights, just so you guys can attend even when you're working. And you can use, there's a discount code for you guys to use the CPS Live. And if you're looking for any other training, please shoot us an email. Here's our email right here, info@elephant-scale. And also, like I said, please sign in for the learning series so you guys will be notified for future classes. All right, so that's that. And again, so this is basically us. Mike is going to be the main presenter today. So Mike has been doing data science, and he's a very experienced data scientist. And you guys are going to see the way Mike presents, how well Mike presents some of the concepts, right? So I'm a big fan of his teaching, and you guys will see too in a second. And his LinkedIn and his email are here. This is me. I'm a founder of Elephant Scale. Like I said, we run corporate trainings on AI and big data technologies, and also my contacts are here too. So let me talk a little bit about this particular series we are launching. And one thing I should say is we had tremendous response for the series. Because if you look at a lot of the machine learning classes, a lot of the machine learning classes focus on how to create a model, right? And they kind of stop right there. Like if you create a model, you did some training, and that's it, it's done. But as anybody will tell you who has done machine learning in real life, that's just a start, right? There's a whole lot of work left right after creating a model on how to take the model, how do you test the model, right? How do you monitor, how do you take it to production? And that's what this series is going to focus on. Because a lot of the time we see this, like, the work left after the model creation is kind of ignored. And this kind of creates a lot of gaps. So people say, yes, I understand how to create a model, but I'm not very sure how to deploy and test and maintain the model. Right? So that's what this series is going to focus on. And again, given the circumstances, we are running this as a free series. So we'll do this as a weekly series for the next few weeks. And if you just look at the session information, right? The link is in the doc. So we actually have first 2 ones defined. This is session 1 you guys are attending today. And then also next week, we are talking about more like how to streamline training. So today, we are going to focus more about TensorFlow2. Right? So Mike is going to go give a tour of what changed, what are some of the cool features, and also show you some sample code so you can get up and running. Right? Again, the intent is not here not to teach deep learning, but to show you guys sort of the missing gaps, right? And I'll show you guys some of the practical and best practices way of doing this. So that's that. And the next one is going to be how do you streamline training? So check this page, and we'll be adding more series once per week. All right, that's that. What else? I think that's pretty much it. So one thing I like to do right now, very quickly, I like to see, know a little bit about your background. So if you guys would do me a favor, here's like a little link I'm highlighting. If you would, go ahead and take a quick background survey because we like to see who's attending, and we like to sort of customize the presentation to sort of fit your background. So if you guys would do me a favor, here's a link, the one I'm highlighting. And also let me put this in the chat window as well. So you guys will get this. Let's take a minute. And if you guys would fill this in for me, and we'll move on. All right, and Mike is ready to go, I believe. So as soon as we are done with this quick survey, we are ready to go.
Ready when you are, Suji. Let's give him a minute to finish up on the survey, and we'll get rolling.
That's right. That's right. Yep. Yep. So let me see. The surveys should be coming in now. Right. All right, I see the results coming in, and I'm sharing my screen, so you can see this too. Yeah, there we go. Yep. So the link for the survey, guys, is in the chat window on the Zoom, and also in the class notes. Excuse me. If you scroll down a bit, you see what I'm highlighting here, right? Just simply click on that to get to the survey. Yeah. And also, guys, we are keeping this on mute just to keep the lines clear. So if you have any questions, the best option is type in the chat window. And also there's an option to do Q&A, right? So you can type your question in the Q&A window as well. And we will once in a while, we'll kind of I'll look at the Q&A panel and we'll answer the questions, right? So.
Mm-hmm. And I've got the question screen up and ready to go on a separate screen here. So as they do come in, I will see them. I'm happy to answer them as they come through.
Gotcha. Yep. Perfecto. Yep.
Sounds good. Okay, cool. Let's. Are we ready, Suji? Should we jump right into it?
I think we are good to go. So again, so just to kind of show you guys, here's a distribution we are getting, right? You guys are seeing this. We got about about almost 30 responses. That's great. So let's see. Most of you are from a developer background, and we are seeing sort of managers, architects, and a couple of data scientists as well. So that's good. I think we have a pretty good mix of folks here. So that's good. And let's see. And then this is sort of the language matrix we look at, right? So the one thing I sort of look at mostly is Python, because as you guys know, this series is going to be focusing on Python. And I can see majority of you are reasonably comfortable in Python. And also we'll give you some Python resources for you guys if you need to sort of, learn a little bit about Python. Yep, very good. And then finally, most of you on Windows, Mac. Okay, very good. So majority Windows. And look at the cloud experience. And this is important because we want to actually target what cloud platform we are going to be showing you guys. So it looks like AWS has a pretty good lead. Very good. And Google Cloud and Azure. Okay, very good. Excellent. And finally, yes, right? I mean, yeah. So, yeah, we don't want to forget this. Yes, ice cream. Yeah, I mean, yeah, I'm with you guys right there. So good. So thank you so much, guys. Again, this is for us to kind of, give you a little bit of background. So thank you for filling out this. All right. So without further ado, I'm going to hand it over to Mike. Mike, all yours.
All right. Thanks, Suji. So I'll start my video now. Hey, everybody. My name is Mike Kane. I am really excited to talk to you all today about TensorFlow2, about deep learning. It's something I'm incredibly passionate about. I've been playing around with it since TensorFlow1 came out here, and it's really changed and grown into what I think is a really great framework. So today, our goal is to get a good feel for what we can do with TensorFlow2. Now, we're going to start small. And in future series here, we're going to do one of these every Thursday. We're going to ramp, okay? So I'm going to provide a lot of resources. If you've got some experience with deep learning, today might seem a bit slow. I encourage you, please stick with it. I'm going to try and make sure I drop in some tidbits for the people with a little bit more experience, a little bit more practice. And again, I'm going to try and bring everybody else up to your level so that by session 2, session 3, session 4, we're doing some really cool stuff and everybody's on the same page, okay? So I'm going to go ahead and share my screen, and we will get going here. Okay, let's see here. And I do want to keep these questions here. Okay, thanks for letting us know, Charles. I appreciate that. We'll make sure we take a look at that link here for the SciPy lectures. Cool. So let's jump right into it, shall we? So can everybody see my PowerPoint presentation okay? Everyone see that? Okay, I see some yeses. Awesome. Cool. So today we're going to start off by talking about what TensorFlow is. What is it used for? More importantly, when would you most likely make use of it? What things can you do with it? And then what things should you maybe use something else for? Okay. Some of you all might have some experience with TensorFlow1. So TensorFlow2 is a new change. It is something that has happened in the last year. And it is as big an overhaul of a software paradigm as I've ever seen. So TensorFlow1, we'll get into it, but it was much harder. It was more configuration than a convention. And they found they were losing some ground to PyTorch from Facebook AI research platform. And they made some changes. They listened to their community. And I think they're in a really good place right now. So today we're going to start off by doing a couple things. We're going to talk about building a nice quality data pipeline using TensorFlow datasets. Now, you've probably got some experience with machine learning. If you're interested in deep learning here, you might have seen some code or run some models yourselves here. You're probably used to doing a lot of the data pre-processing yourselves, splitting your data into training and testing sets, downloading this benchmark data set. Where is it? Okay, now chop it up with NumPy. We're going to see how we can use TensorFlow datasets to make our lives a lot easier. And I think that's one of my favorite parts of it here. We'll also talk about some of the technical implications about that. Then we're going to jump right into building a model with TensorFlow here. We're going to tune that model. And I've got a lot of stuff on here. Chances are we won't go through all of it today, but that's okay because we're going to roll over into the next series. I'm going to spend a ton of time talking about GPUs and TPUs. I will, however, show you how you can get free GPU and TPU time with Google Colab and why that might be useful to you all here. Okay. We'll certainly leave time for Q&A at the end here so that you guys can talk if you prefer to talk rather than type here. I'll try and make sure there's at least 15, 20 minutes at the end for me to answer any questions directly. Okay, so let's jump right into it. Okay, there is a link to a Google Colab notebook in the document, and I would like you to go ahead and go there. You'll also find it in the folder, the Google Drive folder that is shared in that document there. A lot of ways to get here. If you prefer to run this on your local machine, we have a Git repo. You can do that as well. You will need the correct version of TensorFlow and TensorFlow datasets installed. Okay, so anything 2 or above is great. 2.1 is typically what I'm working off of here. Looks like Google Colab itself is running 2.2. Which is the fancy stuff. Not going to make a material difference for what we're doing today. So I'm going to go ahead and give everybody a minute. Go ahead and open this up here. Now, you'll find that this Google Colab notebook, you do not have edit access to. There's a good reason for that, because this is basically the Jupyter Notebook version of a Google Doc. So if you all start typing in this, it will change it for everybody. So in order for you to follow along, if you want to live code with me and work through this here, you need to make a copy, okay? And I'm going to show you how to do that. So if you're in this Google Colab notebook, we're going to go to File, okay? And you're just going to save a copy in Drive, okay? That's all you're going to do. You can also open it in Playground mode. I believe it will bring it to your own version. That's a Playground here. You can either save a copy in your Drive, and then you'll have edit access because it'll be your copy, not the shared copy that I'm using and everyone's using. Or you can open it as a Playground here. Either of those will work. You should have edit access there. Is everybody with me so far? So the Colab link is going to be in this document. Whoops, I can't see it because of the Zoom link here. Let me move this stuff around. So if you go in this document here, I'll drop a link to the Colab notebook here in the chat.
Sorry, Mike. Yeah, I was going to say, if you could sort of go to the shared link right there, you just had it open.
Oh, share. There we go. Yep, that's the one we need.
Yeah.
We will copy link. Okay, so I'm going to do this a couple ways. I will drop this in the webinar chat on Zoom. I'll add this to the link here. Apologies, I didn't realize I didn't add this down here.
So right there on the first page, guys, you will see a class folder right there, right at the last link. Like
right here.
Highlighting. Yep. If you just go there, we click on the link. This has everything you guys need, including the the presentation Mike is doing right now, and the Colab, the notebook. Right? You simply click on the notebook, and then it'll open Colab. So is everybody kind of clear on how to get here, please? Yeah. From your class notes again, Mike. If you could demo it one more time from the class.
Yeah,
notes.
sure. Yeah. Let's do that. So we're right back here in our class notes. We're just going to go to class folder. We're going to click on the link that it opens up here. It'll bring us to this shared Google Drive that everybody has access to. That's for our class today. And you'll see this middle one here, ES Introduction to TensorFlow2. This is the Colab notebook. And then the slide deck, here's a copy of it too here. So all you need to do is double click that and it'll run it for you here. You can open it up in Colab here, okay? And that's an easy way to do it. I've also dropped the Colab link in the Zoom webinar chat. Has everybody been able to get an access to that now? I'm going to go ahead and assume that we are cooking with gas here. I see some yeses. I see some no's here. Okay. No's, are you having trouble? Or you can't find the link? What's the blocker here? Take your time, guys. We're not going to rush here. We'll make sure everyone gets it up here. I can't find the document. No worries here. So the document, it should be dropped in the chat link here at the very top. But I'll go ahead and drop it in there again. Okay. So here's a link to the Google Doc where we got all those from. Okay. And give you the image. That's strange. You'll need to open it with Google Colab is what you'll need to do here. Looks like it's doing that for me too here. Weird. Okay, cool. Well.
Right. So Right. So yep, there we go. So Mike has a link to the class notes. So basically, if you scroll on the top, that this is also emailed to you guys, the tiny URL link. But Mike is going to give you a copy as well here. All right. Yeah. So and then
the tiny URL link right
exactly,
up top there.
That's a guy. Yeah. And basically, I want everybody to basically come here, and everything you guys need is right here. Right. We're going to drop all the links and everything here. And one of the weird things you might notice is like when you go to the class folder and try to open the notebook, it may just give you like a preview. Look all the way to the top. You should see a button that says open with Colab. So
yes, that's what we're looking
I know
for.
it's not very
not intuitive the way they do that.
Not very obvious. So please, yeah, look all the way to the top. You see a link that's open with Colab, and that's what you guys want. All right. You guys type in the question again. Mike will kind of focus on the webinar. I'm watching the Q&A panel. So if you have any issues in the chat window, we will help you through this. Right. So.
And we'll make sure we send a follow-up email to everybody that attended this here. And we'll make sure we include the links to this Google Colab notebook. We'll include the links to the folders, all that good stuff here. So we'll make it easy for you. I do want you all to really focus on paying attention. If you have any questions, feel free to fire them off here. I do want this to be somewhat collaborative here. If you have questions, we can answer them in real time for you here. Or I can certainly, if I don't know the answer, I'll make sure we make a note of it and we'll get that answer to you afterwards here, or point you towards the right direction. So if you can't follow along coding this, not a big deal. We're going to make sure that you get the video, all the other good stuff for this after, and it'll be no worse for wear. So let's jump right into it, okay? So in a Colab notebook, you will not need to run this cell here. We see it's commented out here. Now, let me talk about what we're not going to cover in this here. In order to really take advantage of this particular training here, we're assuming that you all have some baseline level of experience with Python. We are working in Python today. We're also going to guess that you have some general experience with the concept of machine learning. Okay, now we're going to start, as I said, we're going to start pretty basic with that here. I will give some brief reviews here. If you aren't, then it's a bit harder to get up and running with TensorFlow because there's just a lot of knowledge that kind of informs how we do things here. So some of this may seem a bit arcane. That's totally okay. Don't be afraid of tutorials or writing code that you don't quite understand yet. I wouldn't push it to production if I don't understand it, but certainly that's how you learn. Don't be afraid to kind of push that here. For those of you who aren't super familiar with how neural networks work, I've gone ahead and dropped a link here to the 3 Blue 1 Brown series. If you haven't heard of 3 Blue 1 Brown, they are, in my opinion, the absolute best channel on YouTube. This guy is one of the best instructors I've ever seen for all things mathematics and coding. So there's this video series here. In about 3 different 20-minute videos, you'll go from having no idea what a neural network is and how it works to having a really solid understanding of how neural networks are built, how they learn, what backpropagation is, how things like partial derivatives and things like that help that, what a local minima is versus a global, all this good stuff. He does a wonderful job with some excellent visualizations. So highly recommend taking that out. That's at the links and demo section in the bottom of this we put out here. And it opens up this. I'm not going to let this go too long here because you're not here to hear a YouTube video you can watch on your own, but first one here is about 19 minutes, it looks like. Whoops. Let's block that. Get out of here. Okay, so if you're not sure what to do with the theory stuff and where to pick that up, that's a good place to go. This will be very much a practice more than theory session here. So I'm going to start by running this first cell here. And we're just going to import everything we need. It's going to tell us some versions and all that good stuff, okay? So let's go back to this real quick. I want to show you guys some things here as we talk about the difference between TensorFlow 1 and TensorFlow 2, so that as we go back to the notebook, you can kind of pay attention to them and see the difference here, okay? So, whoops, back one here. So as I said, this has been out a little while here. It was originally released in alpha in November 2015, and it was very much built by a team of engineers for engineers. It was pretty hard to use early stage TensorFlow. The way it worked is you would create these static computational graphs, which would literally be every mathematical operation that you need to use, and the data would flow between these operations here. Now, there are a lot of operations that happen inside a neural network. So building a static computational graph of a bunch of vector calculus and linear algebra is kind of hard. It was kind of limiting. So it was really challenging in the beginning. Now, they had a good reason for doing this. The reason they did this was that it made for a really optimized code. TensorFlow is, it was and still is by far the fastest, most kind of crucial, just close to the metal deep learning framework out there you can get that isn't something like CUDA, or where you're programming like directly on the GPUs and things like that. So TensorFlow was a framework to make that a bit easier, but easier was kind of a subjective term, okay? And on the other end of it, you had something like PyTorch, which is the other big dog on the block here in terms of deep learning frameworks. There used to be more. There still are others. There's a ton of other good ones out there too, but these are the ones that people have really circled around. So everyone had to make the choice. Do I want something easy to code in, but not necessarily what I need for production, like PyTorch, or do I learn something that is very, very steep learning curve, but is kind of challenging in terms of getting started and getting up and running here, right? So it was kind of a Faustian bargain to use one or the other here. So TensorFlow is a very interesting team here, and Google has no shortage of great engineers. So one thing that happened was that they had another engineer in their organization named Francois Chalet. If you don't follow him on Twitter, I highly recommend you do. He's one of the most interesting people in machine learning. And he built this library called Keras. So what is Keras? Well, you could think of TensorFlow as like your back end for deep learning, right? Whereas Keras was almost like your front end, right? You very often when we're talking about neural networks, we talk about it at the layer level. We talk about it and we say, well, I want to build a fully connected network. I'm going to have a dense layer with this many neurons, followed by a dropout layer with this percentage, followed by this. We don't want to do all the math for that. We just want to say, here's what I need, go do it for me, right? So Keras acted as that high-level wrapper around TensorFlow. You could also use it around Caffe, Theano, things like that. Other good frameworks here, Theano, Sense Dead in the Water. But this was great, and this was helpful for us, right, for TensorFlow 1. But the issue was now you need to know two libraries. Now you need to know TensorFlow. Now you need to know Keras. One might update and the other didn't, and you could get in all kinds of weird edge cases that was kind of debugging hell, right? So it added a lot of complexity. So the TensorFlow team did the smart thing, and in TensorFlow2, they said, you know what, we're onto something good with Keras. This should be a first-class citizen. We should use the Keras paradigm for everything we do. We should do it in the spirit of Keras, right? So it became a first-class citizen. So the first thing they did is they made Keras itself part of TensorFlow2. You now don't need to, if you install TensorFlow, you've installed Keras too. It's just in tf.keras, right? You don't need to touch a graph anymore, right? You don't need to do that. It used to be you needed a lot of 10 lines of boilerplate to do something as simple as 2 + 2, which I'll show you on the next slide. Now we have eager execution, and it runs a bit more like we're used to running, right? They introduced TensorFlow datasets to, again, really optimize that. They realized that people get pretty good with deep learning, but they may not know all the data engineering to do this stuff here. So you'd be able to speed up your deep learning with GPUs and TPUs and all that fun stuff. But you'd be bottlenecked by how quickly you can do I/O, how quickly you can read your data in and get it batched and all this other stuff. So all the eggheads at Google did a wonderful job putting together the TensorFlow datasets library, and it does a lot of that stuff for us now. So it really speeds up everything. They got every extra ounce of speed out of this thing that they can. So here's what I mean when I talk about eager execution and how much simpler TensorFlow2 is than TensorFlow1. So if you look at the code on the left here, this is what it would do, what you needed to do to get some basic arithmetic done in TensorFlow1. And it's kind of, you can read it, you can figure out what's happening, but it's not very intuitive, right? I would need to create nodes, right? And then I would, like add and subtract, and I would pass in constants or whatever data. Right now I'm using constants, which are a node operation, but yeah, I'm passing them in as data here. And then I would have to go and get this session object, which was everyone's worst nightmare. And you would tell it what nodes you wanted it to run. It would run all the nodes that fed into those and give you your output. This is a lot to do something like what's 2 plus 4, right? Now in TensorFlow2, which is, again, the native TensorFlow you have now, if you're pip installing TensorFlow or conda installing TensorFlow, you're getting TensorFlow2, okay? This is the one on the right here, where I can still declare these as constants. I can also just put them as numbers. I can just go like 2 and 3, and I can do tf.add AB, and it will run it, right? And this is something called eager execution, which if you didn't play around with TensorFlow1, doesn't seem that important to you. But if you suffered through graph hell in TensorFlow1, you're very excited about this. Moving on here, we're going to go, now we're back in our live coding demonstration here. So let's go to our, back to here. So again, everything here is executed with eager execution here. If I run something, it happens. There are still some lazy operations. We'll talk about those and point that out as they come here. But let's jump right into it, okay? So we have imported TensorFlow and TensorFlow datasets here. We've also imported some of the, the usual suspects you'll always use when you're doing data science or machine learning in Python, NumPy and Matplotlib. You don't see pandas because, again, don't really need it this time. I'm going to use one of TensorFlow's datasets. So in deep learning, one of the things that is pretty crucial is you're almost always going to start off by training your network and benchmarking it against a known data set. There are a lot of data sets out there. Now, these are all the ones that are preloaded in TensorFlow datasets. Now, they're not preloaded as in when you install this on your machine, you're downloading all this crap. This is like easily a terabyte of data. These are things that you can use TensorFlow, and you can just pass in this string to TensorFlow datasets, and it'll just go, here you go, and it'll pull it down for you here. So there's some popular ones here you might recognize if you've done some stuff on Kaggle, or you've played around in deep learning, maybe you've taken a course before. You've probably seen like cats versus dogs. CFAR 10 might sound familiar to you, or CFAR 100. Cycle GANs, if you like GANs, oh man, those are cool. We're going to be working today with what is the hello world of machine learning, which is the MNIST dataset. Now, to give a bit of context here, you might have heard of a man named Yann LeCun, and I'm sure I'm butchering that pronunciation. He's French-Canadian, I believe. He is the head of AI at Facebook, and this was one of the first really big things he did that kind of shook the world. Is he figured out I can get a bunch of handwritten digits. He worked with like post offices, and he got a data set of something like 60 or 70,000 handwritten digits. And this was one of the first people to really make good use of convolutional neural networks and backprop. And he built a model called LayNet, which was cutting edge in, I think, 1993 or 96, 90-something. He solved it. It was a really big deal. This model trained for 3 days, and it got to like 80-something% accuracy. And this was one of the first times that everybody goes, whoa, this deep learning stuff is pretty good, because everybody was still really excited about things like symbolic knowledge representation. And it wasn't working, and deep learning hadn't yet come into its own, right? Right now, when we talk about deep learning, or AI, better yet, when we use the phrase AI, everybody who says AI pretty much means deep learning nowadays. There are multiple kinds of machine learning out there. There's evolutionary algorithms, there's symbolic knowledge representation, there's all kinds of good stuff out there. Deep learning, it was invented in like the 50s, right? You could go even back even further to the 40s when they invented this, like a computational version of a neuron. But computers weren't strong enough, so everybody thought these things weren't that good. Well, now computers are strong enough, and it is that good. So we're going to be able to take what was, you know, basically a Turing Award level or a Nobel Prize level challenge in the 90s, and you're going to write it today, and it's going to take you, you know, less than a minute to do so, to train it here. So we've come a long way. All this whole rambling I'm doing right now is to try and make sure you understand just how fast this area moves here, right? So there's a lot of cool stuff, and I encourage you to play around with them here. Not all of them are just for deep learning. You will find like the Iris data set. You will find, here's Titanic, which, you know, everyone cuts their teeth on with stuff here. So let's talk about how to look at what MNIST is here. If you want to see some examples from that here, I thought this was a very handy thing in TensorFlow datasets. So here I have TensorFlow datasets alias to TFDS. I did that on my import. And I can literally just pass in the string MNIST, right? And this is what I just got from up here. It said MNIST. And I'll say, yeah, and hey, bring me the info true. And that's going to give me a bunch of metadata about it. And then I can take this and I can just say, hey, show me it. And it's going to work with matplotlib. And it's going to show me some examples. Okay. So this is essentially just some examples here. We're working today on a data set that these are clearly, that's a 2, that's a 0, that's a 4, right? We can understand what these are. They're kind of grainy and they're black and white. So these are 28 by 28 pixel images, and they're in grayscale. Okay, now that matters. Color images are harder because they have RGB values. We're not going to do that today. We're just going to work with this. Although next week we will absolutely spend some time with convolutional neural networks, working with color images, because those are a bit harder to do, a little bit more complexity, and it'll be a great excuse for us to make use of some free GPU, TPU time from Google, and we'll see just how much faster everything is. Okay, now you'll see in this notebook I have added a lot of information about what the code is doing, what the keywords are doing. You guys, you all know how to read, I assume. So I'm not going to insult your intelligence by reading to you. It is here for notes because I figure you will want to come back to this later and look at it again. But I'm just going to kind of breeze through some of this stuff here and just talk about the code that I'm running. So when I run tfds.load and I pass in the data set name that I want here, I'm typically going to pass in some other things too, like, hey, I want the metadata, give me the info. And I am going to use this for supervised learning. Now, again, there's supervised learning and there's unsupervised learning. And then there's, you know, semi-supervised, which is an entirely different cool new thing that's happening. But what this is basically saying here is when we say is as supervised, this is going to save us a lot of trouble because we typically want our labels and our data to be separate, but we want them in the exact same order, so that the label for the first image and the first, you know, and the first image are the same thing. Because this way we can check our work, right? And that's, at the end of the day, that's how neural networks get better, is by essentially guessing and checking their work and guessing and checking their work, and they can work from that when they figure out which ones they got wrong and which ones they got right. We can even tell it, because again, this is a pre-made data set. Go ahead and split my data into training and testing sets for me here. And that's something that's already pre-computed for MNIST. So if we do that, it'll download this. Now, if you haven't run this before on your machine, it'll take a bit of time to download it here. Let me make sure I run these cells from the top. Otherwise, it's going to yell at me when I try and run them. Okay, and it runs those. And looks like it's already cached. Great. Now, one of the first things we have to do is we have to process our data, right? Anybody who's done a bit of machine learning knows that, you know, you start out and you're kind of green and you're very excited to do some modeling. And you realize maybe 10% of your job is actually modeling. The other 80, 90%, it's gathering data, it's pre-processing it, it's cleaning it, it's all kinds of crap, right? So that is something that can take quite a long time here. So here's the paradigm for doing this with TensorFlow datasets. Create what you need to do, your data transformations, however you're going to pre-process it here, as a function. And then we're going to use map down here on the actual data sets here, the data set objects that train and test things that we returned up here from our tfds.load call, okay? And essentially, it's going to use a functional programming paradigm of, you probably heard of map, filter, and reduce. It's going to use map, and it's going to run this function across all this here. Now, one thing that I think is really, really helpful about this here, and one reason that if I need to do some data pre-processing now, I use TensorFlow whenever possible, even over scikit-learn, because it does things like this. So num parallel calls equals tf.data.experimental.autotune. What is that doing? Well, TensorFlow and the Google team behind it, they are obviously really big fans of making things work fast and of parallelizing any operations possible. So if I need to take 70,000 images and I need to normalize them, and I'll explain what this function is doing in just a second here. Well, I could do that all on one CPU core. Like I almost have every image line up, or every pixel in every image line up, and I divide it by 255, and then I do the next one, and the next one, and the next one. And computers are fast, but that seems a bit inefficient when we realize your average CPU has 4 cores or more nowadays, right? Just about, you can't buy a processor that probably has 1 core. I don't know where I'd find one. So what are these other cores doing? I want them to do some work too, right? It's better to have them all stand in 4 equal lines and kind of go, go, go. So by adding in this bit of boilerplate here, which is I pulled directly from the TensorFlow documentation. I did not come up with that. What this is doing is it's allowing TensorFlow to make an intelligent decision and look at how much can we parallelize this. So it's doing some profiling on your machine under the hood, and it's saying, okay, there's this many cores. Here's how we should split this up. If some lines go faster than others, or some take longer, it's moving them around, I believe. So this is going to make things a lot faster. And I have absolutely noticed that this has had a material effect on my runtimes when I'm pre-processing data. So first pro tip here, use this to parallelize, use TensorFlow datasets to parallelize any data pre-processing you need to do with map. It is phenomenal, okay? So I said I was going to explain what the heck this function is doing. Let's talk about that for a second. In supervised learning, one thing that we find is you want to normalize your images, right? Or you don't want to normalize any data, right? You want to scale it so that it's all on the same page. Well, when working with images, we can cheat a bit. When we're working with, numerical data, let's say it's not an image, let's say it's a, spreadsheet of health data or whatever, and it's all numbers, we might normalize using like z-score normalization, right? We might look at what's the variance here, and then we might say how far from one, and we convert it to standard deviation numbers or z-scores here. We don't have to do that with images because we know images are bound between 0 and 255. This is how we tell a computer exactly how bright or dark a pixel should be. Now, again, we're working with a grayscale image here. So something that is very dark is going to be on one end of the spectrum. Something that's very bright is going to be, up towards 255. I might have those switched. I can never remember which is which. But essentially, so we want to basically shrink these to like a unit level. So one great way to do this, to get them all between values between 0 and 1, which will make our model converge faster and be able to learn a bit better from it, is to just divide everything by 255, right? So this is going to turn it into that. Now, another thing here that I think is pretty crucial, pro tip if you're new to deep learning or TensorFlow specifically, one thing that TensorFlow is going to expect is the typical data type it expects to be passed is float 32. Okay, so here I'm just using a simple TensorFlow function that says, hey, here's my image. I want you to cast, and again, an image is just a list of lists, right? Every pixel is a value. I have 28 rows of 28 pixels each. So it's a 28 by 28 box. So I'm just saying, hey, here's a list of lists, or what we call a matrix or a 2D tensor. And I want you to convert it from whatever it is to this. And when that's done, I want you to divide it all by 255. Now you'll notice labels here too. Why is label here? Well, labels here because in the pre-processing, this is a way to make sure as things get chopped up and moved around through the map call that essentially the image stays with its corresponding label, right? It's the buddy system. So this way we can make sure that, if this is a picture of an 8, the label that says it's an 8 stays with it. It doesn't get lost in the shuffle, okay? But you notice we're not actually doing anything to the label there. So let's go down to what a basic pipeline looks like here, okay? Here, we're just manipulating the train data set here. We're not doing testing yet, although we'll follow very similar steps. First thing I do is I pre-process my data. Now, this is going to be a long-running operation, right? This will not be fast. This is probably going to be one of the more computationally intensive things I have to do in pre-processing my data. So I only want to do it once, okay? And what I'm doing here is just like any, if you play a video games, you beat that hard boss that took forever. What's the first thing you do? You save your game. Well, I'm doing the hard part, and then I'm going to cache. I'm going to save my game, right here. So that cache call is going to say, hey, now go ahead and cache it, store it all in memory. Now, obviously, this becomes harder in the real world if you have a data set that is larger than fits in memory. However, we may talk about this in future ones here. We're not going to talk about that today because most beginners don't start with data sets that are too large to fit in memory, and they have to do partial training on here. Once we've got that, we want to shuffle them here, right? That's just a best practice for machine learning. It's not specific to data science. There could be hidden trends here. It could be that these were alphabetized, right? It could be that they're, in this order or that order, and we don't know that. So what's the best thing to do? Just make it random. Let's go ahead and shuffle all of them here, right? And then we're going to batch them, right? So this is a concept in deep learning where essentially I'm going to work with my data in mini batches because I'm going to do mini batch gradient descent. It's kind of like when you're standing in line, you can go person by person, or I always think of this when you go through the TSA, when you're waiting to get through security at the airport, right? Sometimes people go one by one. Sometimes they say, okay, the family comes up and it's a family of 5, right? Well, that's a mini batch of 5. You can process all 5 of them at once and move on, right? And that's the way we're going to train our neural networks here. We're going to start with a batch size of 128. Now, this is a hyperparameter we can tune, right? The bigger your batch size, typically, the faster you're training. However, there are diminishing returns on that, and it can affect your accuracy here. So this is something, if you want to play with the batch size, you would do it up here, right? And this is going to do all this here. Now, this next line is important, so I'm going to repeat it twice, okay? See how my call ends in a train.prefetch, and I use, this looks familiar. We've seen it before. It's right up here, right? It's what allowed us to do these num parallel calls. It's a best practice to end your pre-processing pipeline when you're setting up your data set to end with a prefetch call. Oh, yes, sorry, Suji, let me zoom in a bit there. Can everybody see that a bit better? Well, that's too much. All right, cool. Now we're zoomed in. So yeah, this is going to make it a bit better. It's going to make it a bit faster here. You always want to prefetch your data. And what this is doing is it's basically telling TensorFlow, go ahead and grab as much, get as prepared as you can for this here, right? So it's going to prefetch those here. Because again, we want to be, there's going to be times where our model is training, but while it's training, it's going to run through that batch. Well, we don't want to sit and wait while the data set goes and gets the other batch together, right? Where we don't want the model to have downtime while the batch is getting together and the batching to have downtime while the model is training. We want them to work at the same time and overlap that as much as possible. If you want to go more deeply into how all this works, or you have some questions or want to see some visualizations about this, I highly recommend taking a look at the TensorFlow datasets documentation. It has some graphs that you can actually reproduce and do benchmarks and all this stuff here to show just how much of a speed up this gets you here. So that's always a wonderful thing to do. And if you're an engineer and you speed things up with this here by looking at some documentation, this is a great way to prove to your boss just how much money you just saved the company. So, hey, this was going this slow and now it goes this much faster and here's how much I saved you. So don't be afraid to kind of lead off on your best foot there. Take a look at some of this stuff, because TensorFlow will make you look really good if you're going from an unoptimized pipeline to an optimized pipeline. I see two questions here. First one from Darshan. Can higher batch sizes cause better accuracy? That is a hard generalization to make. So we're going to see when we talk about the modeling here and training the model here that essentially there's a couple ways you can do this. If I have 100, let's say I have 100,000 items in my data set, right? 100,000 images. I have a couple ways I can do this. I can train on the whole vector of 100,000 at once, which is called gradient descent. I can train on one at a time, randomly selected from this 100,000 without replacement, right? And then I can update the weights. And that's called stochastic gradient descent. And what we're doing is mini batch gradient descent, which is somewhere in the middle. Essentially, we're going to say, hey, I don't want you to do all 100,000 at once and then average what I should do and then make one adjustment to the weights, because that can take too long and it can kind of not be that helpful. And then sometimes doing one at a time can be way too time consuming, and it might make too many weight updates that could make your model thrash a bit. Typically, you always stick your batches to a power of 2. You'll see a lot of powers of 2 here when we do neurons. Can you do a different size? Yes, absolutely. You can do 10, you can do 7, you can do prime numbers, no one cares. The reason you tend to do powers of 2 is because it can help the computer optimize the code when it does VRAM. You know, computers are all powers of 2 under the hood. So for a deep reason that I won't go into, and honestly, I don't really remember, you typically want to stick to powers of 2. It's a good best practice. It won't always make things faster, but it ensures you won't be making things slower. In terms of how it affects your model training, it's going to depend a lot on the task. When you're looking at some models, you might have heard of BERT and things like this. Then for like natural language processing, BERT is super cool. And I'll show you guys the OpenAI, the Hugging Face demo if you want, if you have time at the end here, so you can talk to an AI. But for things like that, they do a much bigger batch size, but they're also training on like 1.5 billion Wikipedia pages. Other times you'll see it's a trade-off, that if you go low here but high, you know, this happens. And if you go higher, it makes it faster, but you sacrifice a bit of accuracy. So there are trade-offs here. There's no real good solid answer here. Unfortunately, I'm not going to be able to give you all on some of these things here hard and fast. This is what you should do, and here's when you should do it. Mainly because this is very new science. We don't know, like mathematically, we can't prove the answers to a lot of these things. A lot of them are best practices right now, where people say, this seems to work. I don't know why, but do this. You'll see that in a lot of white papers right now. Great question. Thank you for that, Darshan. I see another question here. What does the train.shuffle call do? That is an excellent question. So again, this is just like calling a randomize function, okay? So if picture that I had all this data in my train, and again, info.splits is literally just saying, so if we go back up here, right? This data set is naturally divided into 2 splits. And split's just a word they use. We've split our data into training set and testing set. And I know from long experience working with this data set that this is 60,000 images and labels. This is 10,000. Sometimes you just want to test on the train, or just want to work on the train. Sometimes you just want the test, whatever. There's a lot of experiments you can do. So what this is basically saying here is I'm going to the metadata and I'm looking at the number of examples. This is really just telling me how many are here. And I'm going to shuffle all 60,000. So this internal part, if you just ran this part that's highlighted, would tell you how many examples are in your training data set. Because again, I'm calling .splits on info. And this info object is literally just going to tell me information about the data set. It's not the data set itself. So I'm saying, hey, how many num examples, what is the num examples in train? This is going to resolve, the highlighted part resolves to 60,000. And I'm passing the number 60,000 into train.shuffle. So I'm basically saying, I want you to shuffle the first 60,000 items in this data set of 60,000 things. What this does is it makes it random. It's the same reason that we shuffle cards when we buy a new deck, right? You buy a new deck of cards, you got to shuffle that thing because it is in an order, right? And that is a great example of like someone hands you a data set. You may not understand what order it's in or why it's in. Don't assume it's random. You need to make it random yourself. This will not help, this will not hurt your training. It will only help. Okay, so great question there. So let me dismiss these here. Very good. We answered that live. Subasis asks, are we going to have access to the code? Yes, you will. So again, we'll make sure, so you do have this in the link here. If you scroll up in the chat, you'll see the links to this Colab notebook and all that good stuff here, as well as in the document. We will be emailing these after. So short answer, yes, we will. Make sure you guys have all this good stuff to go. So let's keep moving here. So there's going to be a slight difference between how we build out our testing pipeline and our training pipeline, okay? Now, batch size, still going to be the same. Normalization, still going to be the same. We're going to do those things right, okay? We're going to parallelize it, so we still need to normalize. This, again, remember, test is a separate 10,000 images. We just trained and prepared our 60,000 images for training. These are what we're going to use to validate that our model is actually learning and not just cheating and memorizing what all the images actually look like, you know, and kind of cheating the test here. We want to see, does it generalize well the data it hasn't seen before, which is why we're reserving 10,000 images for testing. So everything you do to your training data, you need to do your testing data too, in terms of pre-processing, right? You got to keep them at parity, keep them equal. So we're still going to normalize. We're still going to batch. Now notice, before we cached and then batched. On testing, we're going to do this different, right? On testing, we're going to cut it into batches, and then in comes the carbonite, right? Then we're going to freeze it dead, and we're going to lock it all in place into those batches cached here. You might be wondering why we would do this. Why not do it in the same order with the training one? Well, it's because when we go through and train our model, you're going to see we're going to train this model for like 20 epochs or something like that. That's going to run through the training data a full 20 times if we set 20 epochs, right? Neural networks get to look at the data multiple times. They get to take and retake the practice test, okay? And so we want randomness there. We don't want the first image that it sees in epoch 1 to also be the first image that it sees in epoch 2 and the first image that it sees in epoch 3. We want them to bounce around. I want it to be, okay, number 1 here is number 6,720 in epoch 2, and so on and so forth, right? For training. Now, for testing, we want to be able to compare the performance of how our model did at the end of epoch 1 with how it did at the end of epoch 2 and the end of epoch 3 and all these other things here. And because of that, we need to make sure the test is exactly the same level of difficulty each time. That means that it's the same questions in the same order. So this way, by batching before we cache, we're making sure that when it tests, question 1 will always be the same image. Question 2 will always be the same image. So this is an important thing to do if you cache this here, because if you don't, you know, one of the best questions I've been asked and things like this is, what happens if I don't do that? What mistake, you know, what penalty am I paying here? And the penalty you'd be paying here is that your validation data is not going to be very good. It's going to be all over the place, because you might see it to where, like, epoch 2 it does good, epoch 3 it does good, epoch 4 it sucks. Well, why did it fall apart? Well, it's actually just as good. It just happened to get like a bunch of batches that it did really bad. I got maybe all the hardest questions at the same time, right? Up front, and then it, you know, it's not doing as well. So we wanted to get the same in the same order for testing, because again, it's not learning from our test set. It's only learning from our training set. This way we can kind of do that. And again, our best practice, we end on that prefetch call to make sure that this data is prefetched and ready to go and fast here, okay? Now, you might be wondering, okay, this is great, but Mike, I want to build a neural network, or I want to use TensorFlow datasets to work with data that I have. It's not in their big, long list of stuff. How do I do that? So I've gone ahead, because that's such a common question, and included some sample code. And so there's TensorFlow datasets, which is the library. And then there's the data module, which is inside data TensorFlow. So TensorFlow dot the data module dot a dataset object, right? So you can create a dataset object manually from TensorFlow. And it has a method called from tensor slices. And again, tensors are just, you know, an array. It's a list full of lists, full of lists, full of however many. It's up to you, right? You can you have a vector, then a matrix, and then tensors, you know, all the way down. So this is just a way of saying, hey, I'm going to give you some data and its corresponding labels, and you can just pass this in. So for instance, the Titanic data set. Let's say you prepared it in NumPy and Pandas data frames. You could pass in that data frame because a data frame is just a copy of it's a NumPy array with some extra bells and whistles. I believe you can pass in a data frame here, it'd be fine. If not, you just pass in the NumPy version of it, which is an extra method call there. And the labels, and you'll be good to go. And then you can still do the prefetch call. You can still do the map. You can still do all the other stuff you need to do to pre-process. Like I would do that on train_dataset_example. And I would just use the same code as I did for the pipeline here. The only difference is, you know, this is, if you were going to load your own data set, you would do this instead of the tfds.load call that we had at the top. Okay. So that's a basic kind of version of using TensorFlow datasets to pre-process your data for a model. Now let's get to the fun stuff. Let's build a model here. Okay. So as I said, Keras, that high-level library that everybody loved, has been wrapped directly into TensorFlow. And we see it right here, right? From tensorflow.keras.layers, import flatten and dense. These are layers, right? And layers are what we're going to think at the layer level for our neural network, right? Whether a layer has, whether a dense layer has 1 neuron or 1 million neurons, it's still a dense layer. And it doesn't really affect how I need to do things when coding it, other than just telling it, well, how many neurons does it need? 1 or 1 million or whatever, right? So the sequential object, we're going to start from there. Okay, let me make sure I ran, let's see. Let me run this guy too. Oh, whoops, need to run all these. Oh, I was blowing by stuff too quick there. There we go. Okay, so yeah, that's a huge part of building your models is you actually got to run the darn code. Cool. So I'm going to import some stuff here. Okay. And this is going to be a very simple neural network. I'm going to use flatten. We'll explain what that does in a second here. Dense is the workhorse. It's what you might also hear it referred to as a fully connected layer for feed-forward neural networks. And what is sequential? Sequential is like the skeleton. It's the framework. It is just an empty thing here, and we can pass in layers. We can pass in a name. We can do all kinds of fun stuff here. Okay, so this long couple paragraphs here explains what each hidden layer is doing, what parameters we're going to use, and what they mean. Let's get down to the hyperparameters, because this is a best practice for machine learning engineers. When you train a model, you are not done after training it the first time. You don't know if that's the best performance you can get, right? So you might want to try different architectures. Maybe you have 3 layers or 4 layers or 2. Maybe you vary the number of neurons in them. Maybe you change the activation function or the number of epochs this model trains for. Maybe you change the optimizer and say, hey, I want you to use this optimizer algorithm to learn the weights for this neural network, okay? So I could just specify things like this directly in the code when I create this line for all the talk. These 4 lines, as much as everyone talks, deep learning is hard, it's really challenging. That's a deep neural network, y'all. That's all it is, right? I create a sequential object, and then I go ahead and pass in a flatten layer. I pass in my dense layers. I set how many neurons they have, and that's it. This is very anticlimactic if this is the first time you're seeing a neural network here. Now, what really matters is this stuff. That's where the magic comes in. Because, again, as we said, there's no hard and fast rules. There's no equation I can give you to say, just crunch these numbers, and this will tell you exactly what your neural network should look like. It'll tell you how many neurons it should have. It'll tell you what activation function you have. We don't know enough about deep learning to do that yet, and we may never. So essentially, this is the reason why we all have jobs if we're working in this field, is because we understand how to tune these things and how to practice and make it better and try different things and experiment with them. So if I'm going to train and experiment with a neural network, I'm going to have to run this multiple times, probably over the course of a couple weeks, right? And some of these jobs take a really long time to run. It's not uncommon to see models run for a week on a server full of TPUs. If you're doing like some really advanced computer vision type tasks or things like that. I have some friends that are machine learning engineers at Google, and the runtime stories they tell me are absolutely insane. So you want to be able to iterate quickly when you do have to type code, because you don't want to be the bottleneck. You don't want to be the holdup. So we pull these parameters out into a separate cell. We type them here. And that way, once we've written the code for the neural network, unless I want to add another layer, I might sneak in another model.add and add a layer. That's the only reason I would modify this code. All the rest, I literally just change some numbers here and I fire away, right? Or maybe I write a script and I say, hey, I want you to try 512 here. And the next I want you to try 1,000, and then I want you to try 200, and you can just kind of script it, all right, and use all those wonderful tools we software developers have to make ourselves intelligently lazy. So I'm going to go ahead and run these hyperparameters here. I'm going to create the model, okay? Now, one of the best things you can do is to get in the habit of looking at a summary of your model. Okay, now we haven't talked about what these actual layers are doing so far. Okay, this is a very small neural network. This is kind of a toy as a neural network here. Okay, now that being said, you all are probably at least somewhat familiar with things like logistic regression or linear regression. You're probably familiar with the idea of a coefficient in linear regression, right? So if I have a data set with 10 columns, if I'm going to fit a linear or logistic regression to that, I'm going to find 10 coefficients, right? Another way to interpret that is that I am finding a decision plane in a 10-dimensional space. Now, when we look at trainable parameters here, if you really wanted to, and you had the time, and you know we're on quarantine, so maybe you do, you could absolutely write out the equation for this neural network. Once it's learned all its weights, you could absolutely write y hat equals, coefficient 1, x sub 1, right, for like the top left pixel. And then plus this, plus that. You could write out the whole darn thing. This is a parametric model at the end of the day, which means you could write it as an equation. If you did, it would have 535,818 parameters. That is big, okay? That is really, really big. Now, how big are neural networks in the wild? Well, what about the neural network someone like Google or Facebook is using? Those approach the billions of parameters here. And again, we're using calculus to optimize each one of these parameters. So there's a lot of math going on under the hood here, which is why it's super important that we write our code in an optimized way, because you're going to find that sometimes maybe this would work, but it's just too big. It doesn't run in reasonable time. A neural network that could give you this perfect, perfect answer, but would take 40,000 years to run isn't helping anybody. Okay. So when I print out a summary, what do I do besides just kind of, gawk at this number and think about how far we've come? Well, I look at the output shapes. Okay. And I make sure they line up with my expectations. When you have to debug a neural network, one of the challenges here is that you'll almost always, one of the first bugs you run into is that a layer got an input shape it didn't expect. These things break very easily if the shape isn't exactly what it expects, because then it's got basically null values that it's trying to do math on for the empty spots. So first thing I look for is well, what is this network doing, right? Well, we're building a multi-layer perceptron right now, which is kind of the workhorse of deep learning. You might have read about a single layer perceptron, which is essentially a linear regression. If you use the activation function, and it's logistic. And essentially, a single layer perceptron could only do so much because it didn't have all those middle neurons, those hidden layers, and all that good stuff here. But essentially, whether it's a single or a multi-layer here, you have to pass it your data as a vector. So a vector is a one-dimensional list. That's all it is, right? So you can vectorize your data in NumPy quite easily here. Well, our data doesn't look like a vector. Our data looks like an image of 28 pixels by 28 pixels. So how do I take a 28 by 28 picture and turn it into a vector? Well, I could just concatenate them all together, right? I could just say, you know what, just concatenate all of them to that first list here, and that's going to be a list that is 28 times 28 elements long, which is 784. Okay, so what matters there is that, well, I could do that, and you might have done that with you might have done that before with like NumPy. It's very common to do that sort of processing in NumPy, where you call like np.reshape, pass it what you want to reshape it to, and then the size to reshape it to, and it would do all that linear algebra for you and reshape it. A flattened layer does that exact same thing. We can just build it into our network. Now you'll notice the flattened layer expects, it passes something out. It's going to take in something that we actually specify that up here. This is where we're getting the shape. And if you, we could, as it says here, you could hard code a tuple that says 28 comma 28 comma 1, right? So this basically says it's an array of 28 by 28 pixels with one value each, or a matrix of that. Or we could do this. Now this is a good best practice here, because now again, the feature is called image in the MNIST data set. It will not be that for every data set. It depends on what the column's called. So you have to be able to go into the code and do that, but that's as simple as looking at the data frame if you're loading your own data, or looking at the feature maps if you're using one of theirs. And this dot shape call will get you what you need. This is why that info object we got is very useful. Okay, so we have to tell the flatten layer, hey, here's the input shape. You're going to get an image. It's going to look like this, and I want you to squash it all into a vector. And we see, oh, this works out with our math. And when you squash a 28 by 28 vector, it comes out to a 28 by 28 matrix. It comes out as a 784 vector, right? And that's going to get passed along here. Now, again, there's no learning done here. A flattened layer is just a reshape. It doesn't. There's no neural network part to this here. It's just a tool we built in to make our lives easier. So we're going to look at these, and we're going to make sure these all line up with what we expect. And when you have errors, this is where they'll be, almost always. Okay, so let's run this here. I see a good question in chat. It says, how do you create a TF data set? From Ranga, that's an excellent question. So you can do that. You can absolutely create your own data set and upload it to TensorFlow datasets so that it's stored there. You can absolutely do something like that. You can do it in your own code. That is outside the scope of what we're going to chat about today. However, it's quite easy to find on the TensorFlow datasets documentation. I believe they have it on the main page. You can see the stuff on the left there. So they have all the boilerplate code. You can literally just use their code to do it. But that is something you can do. If you don't want to have to write a bunch of code and load it every time, you can absolutely create your own TensorFlow dataset. It's a great question. Okay, so we've created our model. Up here, right? But it doesn't exist yet. So we explained what we want our model to look like in the term of layers. Well, remember, this is TensorFlow, and under the hood, the reason TensorFlow is so magical is because it builds this incredible static computational graph under the hood for us here. That computational graph doesn't actually exist until we run model.compile. Now, you're probably wondering what some of these things are, right? Loss, optimizer, and metrics. You're going to have to tell it this every time you compile a model. The loss is something you won't have to mess with a lot when you're learning, because that's going to be generally determined by the type of problem you're solving, right? If you were doing regression, you might use something like mean absolute error, or mean absolute percentage error, or root mean squared error. You've probably heard of a lot of these. If this was a binary classification problem, you'd use binary cross entropy. This is a sparse categorical cross entropy problem, so we use sparse categorical cross entropy. One of these things is, it's either the number's either a 4 or it's not a 4. It's a 5 or it's not a 5. It's not. There's no answer that's going to come out where it's correct that it's 80% a 4 and 20% a 5. Right, so it's sparse in that respect here. So this is a mathematical function that other people came up with. This is not me or TensorFlow. This is this is very much in the world of academia. It's a very tried and true loss function, but this is determined by the type of problem you're solving. Now, activation, that's something you can have some fun with, and that's something you can go quite deeply into. We're going to start with sigmoid. However, I encourage you to use this to do things like essentially like ReLU or TANH or things like that to try and get better performance here. I see another question come in here from Subasis. It says, so you are saying that it is based on heuristics or experimental nature to arrive at the optimal model rather than a function, as there's no way to employ a deterministic approach. This is due to the fact that it's difficult to explain why DL works well with certain data sets without a scientific set of equations or theorems. Proofs for lemma as a result of not explaining why DL learning works. Yeah, kind of. So what I'm saying here is that essentially we understand what it's doing to a point here, but the intermediate layers are not human interpretable, right? So when you're building a neural network, and this is something the 3 Blue Brown, I highly recommend those 3 Blue 1 Brown videos because he goes quite deeply into what we can and cannot know from this. But your neurons, you know, you're just trying to learn the right weights. You start off random, right? We literally just pick random numbers out of the air for what the weight should be, for how much each neuron values the inputs it's getting, which are in turn outputs from the neurons in the previous layer. Well, the issue here is that because they start randomly and they get there through gradient descent, we don't actually know what it's learning, right? And it can be somewhat brittle at times. Other times it does past human performance on certain tasks here. But it's not going to work like we're probably used to thinking with something like a decision tree, where if you had to, you could sit down and do the math by hand. You could calculate Gini or entropy and understand why it made the decisions that it made. Now, you could absolutely look at this and say, well, okay, here's the math, right? Here's the weights, and here's why I can track this back. But what that means isn't human interpretable, right? We have some thoughts, we have some theories. This is a very active area of research, probably one of the most active in AI right now is machine learning explainability, specifically deep learning explainability. However, we don't have a way for that. And for that reason, you'll see in areas like in America for, there's certain areas for like maybe healthcare or like credit, I know is a big one that's a regulated industry. You can't just have an AI deny somebody a loan. You have to be able to tell them why, right? So in that case, even though neural networks do really well on this, they cannot use them because we can't prove that it's fair. We can't prove that it works, and it is being fair here, even if it does 93% better at predicting than humans or whatever. There are times when you care about results and there are times where you care about process. Neural networks are great for when you care about results. If you need a fully explainable, transparent process all throughout, then unfortunately deep learning is not quite there yet. There are some cool libraries and tools like Lime or Anchor models. This is actually by the same guy that built Lime, to kind of help explain how certain things change and maybe feature importances. But neural networks are kind of a black box model. They are very, well, they're not kind of, they are a black box model. They're kind of called that. So, so let's run through this here and kind of keep on track. So we're going to compile that model, but very good question, Subasis. Thank you for that. We're going to compile that and then we're going to run it. Now, this is the fun part, okay? When you see it doing this, that means that your code worked. It doesn't necessarily mean that it worked well or that it's going to do well, but it means that at least it compiles, right, or it runs. So we're going to see this thing start to kind of speed up and move here, and we're going to run this for 20 epochs. It should take about, I'd say about a minute. It's getting pretty optimized, and yeah, so first epoch took a while, and that's always the case, and then the second one's going to take about 5 seconds a piece. So just under 2 minutes to run this. Now, what are we looking at as we're seeing this here? Okay, we're getting 4 statistics back here. We are getting, let me move this way so you can see it a bit. We're getting loss, accuracy, val loss, and val accuracy. Okay, now remember we had a training set and a testing set. Okay, a training set, this is the stuff that the model is actually learning for. And by learning, I mean it's allowed to move the weights, right? So it gets something right, cool, don't touch the weights. It gets something wrong, then essentially it's going to shift its weights a little bit. It's going to do something a little bit different. Some neurons might go a bit higher. Some neurons might go a bit lower in terms of their weights and how much they trust or don't trust other neurons before them. The reason that this matters is that eventually it stops learning and starts memorizing, right? That's called overfitting. Now, if you're familiar with machine learning, you know what overfitting is. You probably had some nightmares about it. If you don't know what overfitting is, we can demonstrate it here and you'll learn. Now, it looks like this model isn't overfitting yet. Let's talk about how we know that, okay? Now, we could just kind of read through this. My loss and my accuracy are on my training set. My val loss and val accuracy are on my testing set. So let's talk about how to interpret these here. Now, the nice people at Keras were nice enough to provide some boilerplate code in their documentation to kind of print out here. So if we go back up to the training here, you see you can call and train a model just using model.fit. And it will train your model, and your model will still be there in memory. However, you will lose the statistics if you don't capture them in a variable. So I like to set a variable called history or training history, and that'll be a TensorFlow callback that has essentially a dictionary of statistics on all 4 of these things across every epoch. And if you keep that and run it down here, you get this lovely plot, okay? Now, it's very important to look at your model's performance. Visually look at it. Eyeball it in a graph form. Don't just look at the numbers. And it's much easier to tell when a model is overfitting. Now, this model is not overfitting. When does a model overfit? A model overfits when you see your testing scores start to bottom out. Like it'll plateau. It won't get any better. But your training accuracy will continue improving almost monotonically, right? And what that means is that, well, it's essentially, it's memorizing stuff here, right? You could take a lot of practice tests for like the SAT, right? First 3 times, you're learning generalizable skills that'll help you in the actual SAT. The 20th time you've been through that practice book, well, you just remember these questions. You're not actually learning anything new. So your practice test scores will go up, but your regular won't. Well, that's essentially what overfitting is for machine learning here. Yeah, let's see here. Moving on. So, okay. We've got this here. Now, the loss is going to be the same way, right? Whereas we're going to expect to see the accuracy going up. And again, if I train this for 100 or 200 epochs here, then we will see this overfit, almost guaranteed. And you're welcome to try that on your own. It's quite easy to kind of see that here. When you do, you will see that it will plateau in terms of testing. It will not with training. It'll keep going. It'll start getting better and better and better, and it's going to lie to you a bit. You're going to say, oh, on the testing set, I'm doing great. Or on the training set, I'm doing great. Like your testing set is really what matters here, okay? And just as accuracy we expect to go up and plateau, we're going to see loss go down and plateau. Loss is a measure of how much did we get wrong, right? So per epoch, if we added up all of the error points, right, that are lost from our sparse categorical cross entropy, where would we land here? And this is kind of a measure of that, what that number is here, right? And we see loss going down. That's good, right? So you'll see times where your model, the accuracy doesn't seem to get better, or your accuracy or your val accuracy, but the loss keeps going down a little bit. That model's still learning. It maybe hasn't learned enough to get the next question right, but to where that would improve accuracy, but it is getting better, okay? So we're almost wrapping up here. We just talked about okay, so let's review what we've done so far. We have we've built a training pipeline, right? We've taken a data set, we've pre-processed it, we've shuffled our data, we used caching and batching in an intelligent manner so that we only have to do long-running operations once. We've gone ahead and built a model. We've set our hyperparameters aside so that we can quickly iterate on them. We've trained the model, we've evaluated it. What's left? Well, inference. If you're training a model, you probably want to be able to use it at some point, right? To get some predictions. So I've gone ahead and grabbed a sample image here from MNIST. This is a very ugly 3, I believe. And let's run this cell, and we're going to use this model to get a prediction, right? And we can see it takes a bit of pre-processing here. Now, typically, this is something we're going to cover deeply in, I think, class 3. So not next Thursday, but the following. Suji will confirm or deny that here. We're going to do one on just shipping models, just how to productionize them, whether you're using a TensorFlow serving module or Flask, or maybe one of the cloud providers, something like, I think SageMaker is personally awesome. I'm a huge fan of AWS. We're going to go ahead and play with some of that here, and we're going to see all the ways to do it. But that's about taking your model and exposing it to the outside world so that people, maybe your internal team or clients or customers, can use it. You still have to write the code to call the model and get that here. So there's a bit of, so right here, I grabbed, for instance, one sample image. This is just to get this one. This is not something you would do every time you train a neural network. This is me normalizing it, because again, we trained this on a bunch of data that is pre-processed, right? It's used to learning for images where every value is between 0 and 1. I can give it something where numbers are between 0 and 255. It won't know what to do with it. It'll do very poorly, more than likely, right? And then I needed to reshape it into the exact size that it has here, which is number of examples, number of images in the data set times 28 pixels times 28 pixels grayscale, right? Once I have kind of reshaped it, I pass it in. I call the model.predict function. Your life is always easier if you wrap that in an array, right? And that's it expects it in an array, because almost never do you ever do one at a time. It expects a list of things here. Now, all I did was, this gives me back a list of probabilities, right? And we can actually look at this. If I go and I just go down here and I say prediction, show me what that looks like. I see this is literally just a Python array, right? And I see a bunch of numbers here. If you count, you'll see there's 10. And we'll see that essentially these numbers line up, right? If you actually took this out of scientific notation, you'd see this number and this number are the same, things like that, right? So that's because we used a softmax activation function, which allows us to kind of say, hey, here's all the things you can bet on. You have 100% to distribute however you want amongst these numbers. So figure it out. And our model, we see that it says, well, I'm going to put 98% of my likelihood on the number 3, right? Which is index position 4, because computer scientists start counting at 0. And we see that it also thinks that, now again, don't be fooled by, well, this one has a 9. Well, it's 9, but to the -6 e power, right? I think this is one of our larger ones right here, right? So it says, it looks like 8 came in second place. It's at less than 6%, right? This says I'm 98% sure it's a 3. I'm pretty sure it's not an 8, but out of all the other numbers, it could be that, right? And we say, yeah, that could be. I've seen worse 8s. So I don't know, right? So that is all that we have for you today. I am going to open this up to questions. Before I do, I want to make a plea to you here. If you enjoyed this and you learned it, you want to keep learning with deep learning, I want to encourage you to do that, okay? And the way you're going to get good at this is by practice. Understanding the theory, doing the math, taking a vector calculus course, or going through like a linear algebra course on Coursera edX, those are great. Those are super helpful. But the only way you get good at this is by using it. Because there's plenty of people who know the theory behind this stuff. People don't get paid to know the theory behind this stuff. They get paid to be able to build it. And building it will help you inform your knowledge of how to do these things, right? Because you'll get to see these things in the wild, and it'll help you connect what you're doing with the theory that you're learning concurrently here, okay? So we've built a couple practice problems for you here, and we will have solutions for these next Thursday. When we ramp up the difficulty a bit here, we start doing some stuff. We talk about how to train your models like a professional machine learning engineer, how to do things like maybe set up a Twilio notification so you get a text when your model's done, how to use TensorFlow callbacks to do things like say, I don't care how many epochs you train till it hits 90%. How to use things like early stopping, how to use TensorBoard. TensorBoard is one of the coolest things you'll ever see. Google built an entire framework that spins up a web server to help you explore your models. It is wild. So we're going to talk about that next week. If you're going to attend next week, and I hope you do, I hope you enjoyed this, then I'd encourage you, go ahead and play around with some of this stuff here. Because we got some practice problems here. The first one, go ahead and try and mess around with some of those hyperparameters here. Do some of that experimentation that I've ranted about here. So play around, change the activation functions to like a ReLU. Play around with some of the optimizers. Maybe add a layer. Maybe try changing the number of neurons in a layer. See how it affects your model. The best advice I ever got was from a senior researcher at OpenAI. He says, the most important thing in his life right now isn't his laptop for deep learning, it's his notebook where he handwrites his results. And I thought this makes a lot of sense, right? This was one of the guys who was one of their senior reinforcement learning researchers. And he would write down his parameters, and it was just his sketch of like, I used these numbers and this was my results. And I used these numbers and that was my results. And allow him to keep it all together here. So I'd encourage you to approach this like a scientist, do some of that, okay? And then once you've got some time playing around with the tools, then take a crack at reaching 90% and try to limit your epochs, right? So one challenge you can always do is how high can you get the accuracy? And then the next challenge you can do is how fast can you get to that accuracy? A model that gets there in 3 epochs is better than a model that gets there in 10, okay? And that is absolutely something that you can aim for, because in the real world, that saves companies a lot of money, right? This training stuff is not cheap. I see a good question there from Cab at the end there about the images we've trained on are grayscale. This one is not. So technically they both are. It's that it was color shifted. TensorFlow is smart enough to color shift them here so that it looks the right way, where the background is black and that is white here. This is what the raw image thing looks like when I'm using matplotlib and just doing imshow on this here. If you open them up as images in like Pill or Pillow or one of those libraries here, you'll see it's that way. I believe I can set something like, I think I set CMAP. Let's try. I think CMAP equals plt.cm.binary, I think does it. Yeah, like that. And it changes here. It's literally just what colors it's attaching to what numbers. But good eye, very good thorough eye there. Good question. It's going to be the same thing. Now, again, to a neural network, this doesn't matter. All this did was change how it's displayed on screen. It doesn't actually affect the numbers that are getting passed in here to this. Very good questions. Okay. So Subhasis asks about Docker and Windows Pro. I ran into that myself for that here. So I went ahead and dual booted Ubuntu and just ran Docker that way, and then it works fine here. However, I would say this, you don't have to use Docker. We did provide a Docker instance to make this a bit easier for you if you're comfortable with it. If you're not, feel free to just use Google Colab. Guys, I cannot tell you how much of my work I do in Google Colab. Even though I'm working professionally as a machine learning engineer, I use this. This is not a teaching tool, or not just a teaching tool. I use this thing all the time. And we'll see next week when you come back. We're not going to have time to get into GPUs and TPUs today, but that's fine because it actually fits pretty smoothly in this class. And we're going to find how we can really build some massive networks, and we can speed them up so they're even faster than the small one we did today. So
very quickly, let me kind of look through the choices. Yeah, hey guys, this is Suji Maniam. Let me quickly share my screen, and I'm going to quickly walk you guys through some of the options we give you guys. Oops, that's not what I want to do. I'm going to share my screen. All right. All right, guys. So you guys are already in this meeting notebook, right? So cancel. Okay. So again, this is the URL we are giving out to everybody. So you can actually come in and all the links are here. So if you scroll down a bit, and I hope everybody can see my screen, scroll down a bit, you see a list for setup instructions. Right? Go ahead and hit that. It's another Google Doc. So this is basically what we use when we run our deep learning classes. Basically, right? Again, so just sorry, question was like, how do I get there? I'm sorry. Okay, so here again, let me paste this link, guys, in your Zoom window, right? Again, this is pretty much the only link you guys need. Everything else, we are actually dropping it in this doc. So let me do it one more time. Here's the class notes. Right? Yeah, just bookmark this link for now. Everything you guys need, we are going to drop keep it here. All right. So just come here. You'll see the setup instruction link. Click on that. And basically, what we are doing is, right? I'm talking about the lab environment. There's 4 options, right? And option A, and this is what Mike and I are recommending. This is the simplest thing there is. It's basically literally 0 setup, and all you guys need is a Google account. And I'll be pretty surprised, if you don't have one by now, right? So we all have a Google account. Use that, and this is a Colab. But if you're a type of person who actually want to sort of setting this up on your own, then basically follow this guide. All right. Again, we are giving you 2 choices there. One is you can set up natively, right? You can set up Anaconda, Python environment, and set up TensorFlow there. Basically, all the instructions are right here. You can sort of follow through them, right? They're clearly marked. So option A, option B, option C. And if you don't want to mess up, you still want to run on a computer, but you don't want to sort of mess up, installing Anaconda, whatever, you can get access to our Docker image. Right? Again, if you sort of look down here, I'm walking us through how to get a hold of our Docker training. So our Docker you have for us, so listed here, it actually has everything installed for you guys. Right? So literally 4 options. I would choose, the least painless of all of them is a Colab. Right, and you guys just saw, Mike was doing, using Colab to demo the lab, right? Because it just works. And one thing, Mike will go into in the next session is you will have access to GPU for free, right? And that's pretty neat actually. So that's a pretty good thing to have. Anyway, so take a look at this, please. Depending on your on your preference, you can choose A, B, C, or D, right? Anyway, so that's all, Mike. I'll sort of pass it back to you. I know you have some questions coming on the coming in, so please go ahead and answer those. Yeah, thank you.
Yeah, sure. Let's open it up to any remaining questions people might have here. So I saw one that I missed here from Subasis saying that balancing overfitting by using generalization, sometimes using cross-val. This can be evaluated when you have high accuracy with testing data versus poor accuracy on holdout data set. And that's definitely a way to tell about overfitting and generalization. Subasis, absolutely, that is a best practice for machine learning. Typically, you don't see cross-validation used in deep learning. Cross-validation, for those of you who might not be familiar with it, is when you say, well, I want to split my, instead of training my model and randomly selecting 10% to be training data, testing data, and all the rest is training. Well, how do you know what 10% you picked? Did you pick the hard part, the easy part, somewhere in the middle? You can't actually know if you're doing it random, right? So one thing that you'll do in more traditional machine learning methods here is you'll say, well, I'm going to break this into groups of into thirds. That would be like a 3-fold cross-validation, or fifths. That would be a 5-fold cross-validation. And then you train models where essentially across rounds, and every round a different group gets to be the test set, and you average results. One reason that's not a best practice for deep learning, particularly the way you might do it with like a support vector machine or a decision tree or something like that, is because a neural network is training on all of the data. So it has seen the test set before. That'll actually give you what we call label leakage, right? So once it's past the second epoch, essentially, anything that could possibly be in the test set, it has seen once before. So you typically don't use that for deep learning. Now, what you will see, and I can tell you the way that companies like Google do this as a best practice, is they do what's called like a train val test set, or a train developer test set, or whatever word it is here. But essentially, you keep your test set, you have your training set, you have your test set, which will be like your val set, where we got the val loss, val accuracy on the model here. And that's the one you'll be using again and again with every different epoch. That's the one you're doing everyday development on. And then you have this one set sitting out in the corner, you know, your test set, right, or your validation set, and you're not using that every time. You get to try that exactly once. Now, this is what they actually do at Google. I have a couple good friends on the TensorFlow team and on their AI teams here, and they talk about how terrifying it is to actually run it on that test set, because for a number of reasons, you can actually overfit to your validation set too, right? So the one that we're getting that on here, you can mathematically, you can prove you might be just accidentally kind of implicitly overfitting on that, right? So you have like two different out of sample ones here. One that you get to see a lot on and you use to benchmark and track your performance as the model gets better, and hopefully. And then you have one where this is the one that is like, you know, you only get one life, you only get one try. And if the model isn't up to performance after that, again, nobody's seen it, nobody gets to try it, the model's never seen it, you don't test with it until you're absolutely done. Very last thing you do before shipping to production. If it passes that, good. You can assume the model is good. If it doesn't, they literally throw it out and start from scratch. So that is a very draconian but effective way of making sure that your model does generalize, because you keep two out of sample sets there for testing. One that you use to be able to tune and train and see how things are going, and one to just say, well, let's put it all on black and see how we do here. So very good questions here. I see somebody asked, is the CPU and GPU of Google free for you to use in Colab, even if you need huge computing? Yes, up to a number of hours it is. So you can actually do that. I'll show you all how to do this real quick here. If you go, I'm going to zoom out a bit. Now, you have to write some code to essentially make use of the GPU and TPU that is on the TensorFlow docs. It is not hard to do. You can very much, some of y'all can figure this out by just going to the documentation. But if I'm in Colab right now, if I go up to runtime and I go to change runtime type, right? Hardware accelerator, I can literally click this drop down and I can say GPU or TPU. We're going to walk you through this next week. Now, again, that, go ahead, Suji, what was that?
Screen share, please.
Oh, crap. I forgot I'm not sharing. Let me pull that up. Thank you. This quarantine's getting to me, y'all. Can you guys see that now? Everyone see that okay? Yeah? I assume that's a yes. So again, let me show you that one more time here. I go to runtime. Okay, so I go to runtime, change runtime type, and it's just right here, hardware accelerator, GPU, TPU. Now what that does, it doesn't automatically make your code run much, much faster. It's gonna run it the same way it would on a CPU, just on a machine that happens to have GPUs and TPUs. You have to write a bit of code. We'll talk about using mirrored strategy, how to get the actual addresses of these devices here, and how it'll speed up your code. It is very simple. We can absolutely walk you through this, and we'll provide plenty of boilerplate code next Thursday for this. That's one of the most important things that we have there is deep learning is good, but you can only do so much without without GPUs and TPUs. So we're going to show how to do that, and it is using GPUs takes a bit of work. Using TPUs takes a bit more. TPUs are harder. However, they're even 10 to 17 times faster than GPUs. GPUs, to give you guys an idea what sort of speed up you get going from CPU to GPU. I've had models that have told me if I run this on the CPU, it'll take 740 hours. And then I run it on a GPU and it takes like hour and a half less. TPU, it takes like 40 minutes. So it has a massive speed up because these are hardware that's built for matrix multiplication. CPUs are not, so they have to chop it up and do it piece by piece. GPUs and TPUs are meant for this sort of stuff here. Very cool stuff there. Well, we'll go much deeper into why this hardware is so effective next time. We'll talk a bit about that, so you can talk about like bfloat 16 data types, systolic data arrays, all that other good stuff. I'll link some videos to it in our next Thursday's class. I hope you join us for that. So good questions here. Subhas has mentioned there is another program which allows you to use GPUs, TPUs as well. Yeah, so you will see this now. A lot of them have lead-in things here. Kaggle, if you all have had some fun with Kaggle competitions before, Kaggle kernels, Google bought Kaggle, and they provide something like 30 hours a month of free GPU or TPU access here. Google Colab itself gives you something like 10 or 20 hours. You can pay $10 a month for Colab Pro, and that will give you a ton here. And again, if you all are doing this on the job, you already have AWS. You know, a lot of like a P2X large or something like that instance absolutely has these built in already. So you just need to look at like whatever cloud platform you're using. If you're doing this on the job, it already has it too. Okay, but I promise we will get quite deeply into all that. If you do have an NVIDIA card in your machine here, like I run a GeForce 1070 Ti. I kind of built my own little deep learning rig. It is helpful. It's faster than on the CPU. It is still wildly slower compared to like a server full of GPUs. So don't, it's helpful, but there's still, it kind of raises that glass ceiling, but there's still one. There's some things you're just not going to run on a local machine. You got to run on a server that has 256 GPUs. Let's see. Do we have any other questions or anything like that we'd like before we wrap? I see one question. During interpretation, is it possible to have large deviation between test and training results? If yes, how to interpret? Srividya, yes, that is possible here. Typically, I would interpret that as, so the first thing I would look for is overfitting, right? So typically what happens is you'll almost always score better on your training set than your testing set. That is a key indicator of overfitting. Great question there. There are other times where this might not be the case, right? If you see, well, it does okay on training, but testing is kind of all over the place. Like you'll see it looks like a heart monitor. The line's up and down and all over the place here. That, almost random. Typically, that's going to show you have some sort of issue. Maybe your labels are out of order in your test set or something like that. There are issues like that is here. That's typically one of the first signs you need to debug. Debugging, unfortunately, is a bit less straightforward for deep learning than it is for like traditional software engineering. There's no debugger you can run and look at variable values because, again, we don't know what these weights are. So typically then you start looking at like, well, is everything in order? Did it match up correctly? Is my pipeline doing what I think it's doing? All that's good stuff. So short answer is yes, it is quite possible to see a deviation between training and testing, and that is your first sign that something is usually wrong, because your training and testing set should come from the same data source, and therefore your model should be able to do just as well on both. If it does better on one than the other, it's overfitting, and there are ways to deal with that. We'll learn about dropout and batch norm next week. But if they're still happening beyond all that, then typically you just got to roll your sleeves up and kind of look at all your code and figure out, got to be clever and figure it out. Great questions. All right, we've got just a couple minutes left. Happy to answer any more questions that come through here. Rajudoma, you are very welcome. Thank you so much for attending. And again, guys, we will absolutely make sure that we send out an email with links to all these resources. The video will take a couple hours to process through Zoom. We will make sure we get a link to you of this recording, however. But it won't happen in like the next hour because Zoom has to give us access to it and they have to do a bunch of processing. As soon as we have that, we have all these things put together, be on the lookout in your inbox for it, and you can have all this good stuff for reference. We hope to see you all next Thursday, so please come on back and we'll teach you all about all the fun stuff we can do when we're optimizing our deep learning and really getting good at it. Cab, you're very welcome. Thanks for joining.
All right, I think we'll end the meeting then. Yeah. Yep.
All right, we got one more question here. Based on Srividya's question, does it not require additional training with more epochs or layers? It seems the model's not converged. Yeah, that could be one reason. Absolutely, model convergence could be the reason there, Subhas. That's a great point. typically, if you see large deviations between training and testing, you expect the learning to happen at the same rate generally, right? Because it's learning generalized features. So you would expect that to do poorly in like epoch 1, epoch 2 on both of them, but you wouldn't expect it to start getting better at training, but then never get better at testing or something like that, right? Or I can't imagine a weird scenario, but I'm sure it exists where you get better at testing but not training. But yes, model convergence could be one thing. This is something where TensorBoard will be quite helpful. We'll take a look at that next week. And we'll talk about how we can tell, is this a convergence issue? What is convergence? When do we converge? How do we detect overfitting? How do we deal with overfitting? And then finally, how do we set these builds to run intelligently so it doesn't, take forever? And we can get other things done and get notified when it's ready. So we're going to have some fun with that. So I think that's the last question we got here. I think we're going to wrap it now. Thank you all so much for attending. This has been a lot of fun. Hopefully we'll see you next Thursday.